Imagine a place where gravity reigns supreme, a realm so mysterious and powerful that it defies our everyday understanding of physics. In the vast expanse of the universe, there exist regions where the rules we know simply break down, and the very fabric of reality is stretched to its limits. These are the domains of black holes, enigmatic objects that have fascinated scientists, astronomers, and dreamers alike for generations. A black hole is a place so dense, so compact, that nothing, not even light, the fastest traveler in the cosmos, can escape its clutches. The gravity here is so overwhelming that it pulls everything inward, trapping it forever in a region from which there is no return. These cosmic monsters, known as black holes, are among the most enigmatic and awe-inspiring objects in the universe. They lurk at the centers of galaxies, including our own Milky Way, and their presence can be detected only by the way they affect the matter and light around them. For decades, black holes were thought to be purely theoretical, but now, thanks to advanced telescopes and groundbreaking research, we have begun to glimpse their true nature. Born from the death throes of massive stars, black holes represent the ultimate triumph of gravity, warping the fabric of space-time and honestly, just captivating our imagination. When a star many times more massive than our sun reaches the end of its life, it explodes in a brilliant supernova, leaving behind a core so heavy that it collapses under its own immense weight. Picture a star, much more massive than our own sun, shining brightly for millions of years. Over time, it burns through its nuclear fuel, fusing lighter elements into heavier ones in a delicate balance between gravity pulling inward and pressure pushing outward. But eventually, this balance tips. As its nuclear fuel dwindles, the star can no longer support its own weight and it collapses in on itself, imploding into an infinitesimally small point called a singularity. This collapse is so violent and complete that all the star's mass is squeezed into a space smaller than an atom, creating a region of infinite density. This singularity lies at the heart of a black hole, shrouded by an invisible boundary known as the event horizon. The event horizon marks the point of no return. Once crossed, nothing can escape, not even information itself. It's as if the laws of physics as we know them simply cease to apply. Once something crosses the event horizon, there's no turning back. Whether it's a star, a planet, or even a beam of light, everything is drawn inexorably toward the singularity, lost to the outside universe forever. The event horizon is a one-way door, a boundary that separates the known from the unknowable. The gravitational pull within this boundary is so intense that even light, the fastest thing in the universe, cannot escape. This is why black holes appear black. They emit no light of their own, and any light that ventures too close is trapped, swirling around the event horizon in a final desperate dance before vanishing. It's as if the black hole is a cosmic vacuum cleaner, relentlessly sucking in anything that ventures too close. Gas, dust, and even entire stars can be torn apart and devoured, their matter spiraling inward in a brilliant glowing disk, before disappearing forever. Black holes are not just destroyers though, they are also creators, shaping galaxies and influencing the evolution of the cosmos in ways we are only beginning to understand. The enigma of black holes continues to challenge our imagination and push the boundaries of science, inviting us to explore the deepest mysteries of the universe. Einstein's theory of general relativity revolutionized our understanding of gravity, forever changing the way we perceive the universe. Before Einstein, gravity was thought of as a mysterious force that simply pulled objects together, as described by Isaac Newton centuries earlier. Newton's laws explained the motion of planets and falling apples, but they couldn't answer deeper questions, like how gravity actually works, or why it acts at a distance. Einstein's insight was both radical and elegant. He revealed that gravity is not a force in the traditional sense but rather a consequence of the way mass and energy warp the very fabric of space-time itself. Imagine the universe as a vast, flexible sheet, what we call space-time. When a massive object like a planet or a star sits on this sheet, it creates a dip or a curve, altering the paths of anything moving nearby. Massive objects such as stars, planets, and especially black holes create deep depressions in this cosmic fabric. The more massive the object, the deeper and more pronounced the curve. This is similar to placing a heavy bowling ball on a trampoline. The ball creates a dip and smaller objects roll toward it, not because they are being pulled by an invisible force, but because the surface itself is curved. This curvature of space-time doesn't just dictate the motion of planets and stars. It also affects something even more fundamental, the flow of time itself. In Einstein's universe, time and space are woven together, and when space-time curves, time bends along with it. The stronger the gravitational field, the more time is stretched and slowed. This strange phenomenon is known as gravitational time dilation. It means that time itself ticks at different rates depending on how close you are to a massive object. In regions of intense gravity, like near a black hole or a neutron star, time slows down dramatically compared to areas with weaker gravity, such as far from any massive body. To visualize this, imagine two identical clocks. One sits safely on Earth, while the other is placed near the event horizon of a black hole, the point of no return. Both clocks are perfectly synchronized before the experiment begins. As time passes, the clock near the black hole ticks more and more slowly compared to the one on Earth. To an observer watching from a distance, it would seem as if the clock near the black hole is almost frozen in time, while the Earth clock continues at its normal pace. This isn't just a theoretical prediction. Scientists have measured time dilation with incredibly precise atomic clocks on airplanes and satellites, confirming Einstein's ideas. The closer you get to a massive object, especially something as extreme as a black hole, the more pronounced this effect becomes. The clock near the black hole would tick slower than the clock on Earth, and this difference grows as you approach the event horizon. This difference in time isn't due to any mechanical malfunction or flaw in the clocks themselves. Instead, it's a direct result of the fundamental nature of gravity's influence on time. The very passage of time is altered by the presence of mass and energy, a concept that challenges our everyday experience and intuition. The closer an object gets to a black hole, the slower time runs for it relative to an observer farther away. This means that, in the most extreme environments in the universe, time itself can nearly come to a standstill. Gravity's relentless grip not only shapes the motion of planets and stars, but also stretches and warps the very fabric of reality, including the flow of time itself. The concept of time travel has long captivated our imaginations, fueled by science fiction stories that stretch the boundaries of what we believe is possible. From the earliest pulp magazines to blockbuster movies, tales of voyagers leaping centuries into the future or revisiting the distant past have inspired generations to dream beyond the constraints of our everyday reality. These stories often blur the line between fact and fiction, inviting us to question what might one day be achievable through science and technology. Our fascination with time travel is deeply rooted in our innate desire to explore the unknown, to reach beyond the stars, and to unravel the mysteries of the universe. As we gaze up at the night sky, we can't help but wonder what secrets the cosmos holds, and whether the fabric of space and time itself might offer hidden pathways to other eras. Among the most mysterious and powerful objects in the universe are black holes. With their immense gravity and ability to warp both space and time, black holes have become a focal point for scientific speculation about the nature of reality. Could these cosmic giants, which bend the very fabric of the universe, hold the key to unlocking the secrets of time travel? Or are they simply insurmountable barriers, forever separating us from the possibility of moving through time? Theoretically, black holes offer tantalizing possibilities for time travel. Physicists and astrophysicists have spent decades exploring the equations of general relativity, searching for loopholes that might allow for journeys through time. While the practical challenges are immense, the mathematics suggests that under certain conditions, black holes could act as gateways to other times or even other universes. One of the most intriguing ideas is the concept of a wormhole, a theoretical shortcut through space-time that connects two distant points in the universe. If such a tunnel could exist, it might allow for instantaneous travel between far-flung regions of space, or even between different moments in time. This idea, popularized by countless science fiction stories, is rooted in real scientific theories, though no wormhole has ever been observed. Some scientists believe that black holes could be the mouths of these wormholes, serving as entry and exit points for travelers brave enough to venture inside. The notion is both thrilling and terrifying, as the immense gravitational forces near a black hole would make such a journey incredibly dangerous, if not impossible, with our current technology. Another possibility involves harnessing the rotational energy of a spinning black hole, known as a Kerr black hole. Unlike their non-rotating counterparts, these black holes twist and drag the fabric of space-time around them, creating unique environments where the usual rules of physics may not always apply. As a black hole spins, it drags space-time along with it, creating a region called the ergosphere. Within this swirling boundary, the effects of gravity and rotation combine in extraordinary ways, opening up theoretical possibilities for manipulating time itself. Within the ergosphere, it might be possible to enter a specific trajectory that would allow you to travel back in time, at least according to some interpretations of Einstein's equations. While these ideas remain firmly in the realm of theory, they continue to inspire scientists and storytellers alike, reminding us that the boundary between fact and fiction is often just a question of what we have yet to discover. While the idea of using black holes for time travel is, really intriguing, it's important to note that we are venturing into the realm of theoretical physics. The scientific community remains divided on the feasibility of time travel, and honestly, many challenges and uncertainties remain. One of the biggest obstacles is the sheer power of black holes. The gravitational forces involved are so extreme that any spacecraft or human attempting to approach a black hole would likely be ripped apart by tidal forces, a phenomenon known as spaghettification. Furthermore, the existence of wormholes and the ability to harness the rotational energy of black holes are purely theoretical concepts. We currently lack the technological capabilities to test these ideas or even to observe black holes directly, relying instead on indirect evidence and theoretical models. Even if time travel through black holes were possible, it would be a perilous endeavor. The environment near a black hole is incredibly hostile, fraught with intense radiation, gravitational forces, and unknown phenomena. As an object approaches a black hole, it experiences intense tidal forces stretching and compressing it along different axes. This spaghettification process would be fatal to any spacecraft or human, stretching them out into long thin strands like spaghetti. Moreover, the accretion disk surrounding a black hole, which is a swirling disk of gas and dust, is heated to millions of degrees by friction and gravitational forces. This intense heat and radiation would incinerate anything in its path. While the prospect of using black holes for time travel remains highly speculative, the pursuit of this knowledge continues to drive scientific inquiry and, honestly, ignite our imaginations. The universe is full of mysteries waiting to be unraveled, and black holes with their enigmatic nature hold clues to some of the most fundamental questions about the cosmos. Future advancements in theoretical physics, observational astronomy, and space exploration may one day provide us with a deeper understanding of black holes and their potential for time travel. Until then, we can just marvel at the wonders of the universe and continue to explore the boundaries of human knowledge.